Here we are about to start practice problem number 2. In this video, we'll do practice 2 and 3. So, all right, hopefully you read the little bit, uh, uh, in the lecture between practice problems 1 and 2. So just to summarize really quick, the cautions on the central limit theorem. So the idea is that the central limit theorem turns things that are not normal into distributions that are normal using the sample means, right? So what we have to be careful about is that the sample size is big enough. The idea that caution really is just explained. If the sample size is not big enough, then those averages are not going to be based on something powerful enough to make the new distribution normal. So the rule is you need a sample size of 30 or more. If your distribution, your original distribution, is not normal, or if it's unknown, then you need at least 30 in your sample for the central limit theorem to work. If you use anything less than that, then we can't go about it this way. Now, kind of in that sense, it's nice. We're never going to get a problem that gives us a non-normal original and then a sample size less than 30, because it has to be more than 30 in order for us to apply this formula and the z-table and all that. But the one thing to keep in mind, and it says there, if the original distribution was normal, if it was normal to begin with, then it's already normal. It already looks that way, and we don't have to have this restriction of at least 30 in the sample. Okay, so we're going to see, that it's going to kind of come up once in a while in the problems, but then even just knowing that concept is really, really key. Okay, so let's go to practice number 2. It says the Nielsen television ratings, very famous TV ratings, and I remember hearing about them a lot when I was growing up. For different shows and things. So the Nielsen television ratings reported that children between the ages of 2 and 5 watch on average 25 hours of TV per week. When I read that the first time, I thought, oh, that's so sad. 25 hours, that's over a day of TV in the week. But that boils down to like somewhere between 3 and 4 hours a day. And like, oh, well, that's really not that bad at all. Okay, so the variable is normally distributed with a standard deviation of 3 hours. If 24 children between the ages of 2 and 5 are randomly selected, find the probability that the mean number of hours they watch TV per week will be greater than 25.5. Okay, just barely bigger than the average of 25 hours. All right, so let's try and name each of our variables here. I've got it all laid out for us. So what is mu here? And if we were in class, I'd say, what is mu, everybody? And hopefully, probably one or two people would say, well, they told us the average is 25 hours. Okay. A little bit later, it says the standard deviation is 3. And then to begin that last sentence, it says if 24 children between the ages of 2 and 5 are randomly selected, which means n is 24. 24 children selected. What's the probability that the mean number is greater than 25.5? So we're going to take x bar to be that value in question, the 25.5. Okay, now at this moment, you might think to yourself, wait a second. That n, it's less than 30. You just said that for this whole theorem to work, that n has to be at least 30. Well, in this case, it doesn't have to be at least 30 because it says the variable is normally distributed. This is okay that it's less than 30, since you would say the original population is normal or is normally distributed, right? They tell us that. It was normal to begin with, so we don't need a sample size of at least 30. If it's normal to begin with, we don't have to turn it into something normal. Okay, you get the idea. So we're going to take these values and we're going to plug them all into our formula, and I'm just going to show you all this. We've got our x bar minus mu over sigma divided by the square root of n. If you want to just go for it here in your calculator, just be sure to use those parentheses, or maybe you want to do that subtraction in the numerator. This is not a nice square root, so probably just going to leave that. Use parentheses there. In any case, confirm that you get 0.82, and that is rounded to 2 decimal places. I think it's actually 0.819 or 0.1818 or something like that. So we got to round that z-score to use our table. Okay, so far so good. Now we're going to do the probability with our z-score. And now this is a key step in the problem. So I haven't shown you a whole lot here. We know it's going to be probability capital Z. We're going to put the 0.82 here. But which symbol are we going to use? Is it going to be a greater than? Is it going to be a less than? And if you go back and read carefully that last part, the probability that it will be greater than 25.5. So we need the greater than here because we read greater than, probability greater than is what they're asking for. What do you do if they're asking for a greater than? Like, well, my table only tells me less than. So I believe we had these in chapter 6. We're going to use a complement. If they want a greater than, we're going to do 1 minus the probability of it being less than. So we're going to find the opposite, but then subtract it from 100%. And there's our complement rearing its head again. Now this we can look up in the table. Okay, so we're going to grab our table. We're on the positive side. We're going to look up 0.82, 0.7939. And we know we've actually got 1 minus that, 0.7939. And now doing that subtraction, boom, there's our answer, 0.2061. Now, if you haven't caught on yet, I'm all about the graphing because it really helps me visualize what I just calculated. So if we were in class, I'd definitely be doing this as well. So we've got this steep normal distribution because we are doing these samples. They told us the average was 25, and we only strayed out just a little bit, 25.5. It's probably actually closer than that, but just so I can fit it all in. They were asking for the probability greater. What is that area? What is that probability there? And so we figured we need to find all of the area that's below it. That's what our table tells us. That's the 0.7939. But then if we subtract that from 100%, then it will give us the part that's left over. 20.61%, 0.2061. Okay, very nice. That is practice problem number 2. Let's go on to number 3. Okay. So I'm just kind of, I think we can get all this off the screen. Yeah, all right, let's go for it. Okay, so there's 3 parts to this one, but they're all very similar, and they're kind of getting at, the idea is to get you to compare each situation. So number 3 says the average amount of meat that a person in the U.S. consumes per year is 218.4 pounds. Well, over 365 days, I mean, that's not even a pound a day. Any vegetarians, vegans out there, in the class. I'm with you. Maybe you read that and that's offensive. Over 200 pounds of meat per person on average. I was a vegetarian for over 4 years when I was in my 20s, and I really respect that lifestyle. Um, so I get you right now. Okay, but the rest of us, the rest of you meat eaters, um, let's keep reading. So the standard deviation is 25 pounds, and also here the distribution is normal. So we're not stuck with the limitation of 30 of our sample size. Although if you keep reading in part A, a sample of 30 individuals is selected. Well, okay, so we still got that sample of 30. Find the probability that the mean of the sample will be less than 210 pounds per year. The mean of the sample less than 210 pounds. Okay, so let's go ahead and fill in these values. Maybe you already are as we're reading it. So it says the first thing they tell us is the average in the US is 218.4. Standard deviation is 25. Okay. Then in part A, a sample of 30 individuals. And we're investigating 210 pounds per year. So that's our X bar. All right. I've continued this on the next page. At this point, I'm just going to plug all that in. Okay. And now hopefully we're getting familiar with this. X bar minus mu divided by sigma, which is divided by the square root of n. Again, be sure to use parentheses there if you just are going to attack it in your calculator right here, or if you prefer to simplify that numerator, be sure to still use parentheses in the denominator. And that gives us a negative z-score. It's the first negative we've seen in this chapter, but we saw them before. And that's, of course, rounded, negative 1.84. So, taking that z-score, we'll find the probability. Now, what symbol, this time the probability of capital Z, sorry, that looks like a little z, it looks about the same size, that's a capital Z. We'll put our z-score in. Which symbol do we want? What did they say? They said less than 210 pounds. So nothing special here. We don't have to use any complement. We can just go for our Z table right now. And here I am on the negative side. What was it? Negative 1.84. Negative 1.84. Negative 1.84 right there. 0.0329. 0.0329 is the probability. And that's it. That's our answer. Very nice. Okay, so really so far doesn't feel very different from even the first practice problem that we did. What's the point here? Okay, so in part B, it's kind of a comparative sort of example. So part B, the only thing they change is now the sample size is going to be 40 and not 30. So if a sample of 40 individuals, find the probability that the mean of the sample will be less than 210. So that part's the same. Still taking 210 as X bar, it's still less than. We make the sample size a little bigger. Okay, so if we were in class, I'd pause here and I'd say, hey, so if we make the sample size bigger, is the probability in the end going to get bigger or is it going to get smaller? If the sample size is bigger, does that mean it's going to be more likely to get our average to be less than 210? Or is it less likely that our average is less than 210? So I'd put that out to the class, and maybe one or two people would know what it is. But I don't think I would answer at that point. I just kind of hear you guys out, and then we'd proceed. Like, okay, well, some people maybe think it'll be one, some people think it's the other. Let's see what the numbers say. So we'll take everything and we'll plug it in, right? Of course. Just go about it the same way, putting everything in there. Right? Highly encourage you guys, grab your calculators, have them ready while we're doing these together. Make sure you get that answer. It would be a tragedy to know the formula, know all the concept, but you forget some parentheses and you end up not getting the right z-score. In this case, it's negative 2.13 when it's rounded. And we'll look that up. It's still a less than, so I just went ahead and put that in. Although I don't know the final answer. Let's see. I'm not going to bring my table up on the camera. I'm just going to do it right here. And work along with me, please. Negative 2.13. Negative 2.13. Did you get 0.0166 as the answer? Okay, that's it. Just barely more than 1%, 1.66% chance of this happening. What was the previous answer? It got smaller. It's less likely. Oh, wow. Okay, so if the sample size is 30, there's the chances. Make the sample size 40, it's like half the size. How did that happen? Well, it's kind of back to that argument of, when we take sample sizes, it pushes the data into the middle. So, maybe the original normal distribution, it says this was originally normally distributed, was like this. So then when we did our sample size of 30, it's pushed, right? There's n equals, I don't know where I'm going to be drawing these, because it's all going to be running on top of one another. There's our n equals 30. Here's the original. When we did a sample size of 40, it pushed it in even more. So it really squeezed it. And mine's all lopsided a bit. Okay, so our average in the middle is still that 218.4. But now as we venture down and find the probability at 210, say, yeah, if we're really squeezing it, this compared to the original, right? This amount versus all that. The higher the sample size, the more it's squeezed, and the probabilities drop as we get further away. Okay. Hopefully I've made my point there. So what is part C of this problem? Now part C is at the top of the next page. Part C says, find the probability that one person selected at random consumes less than 210 pounds per year. One person selected at random. Well, what's the sample size here? And you're like, oh, well, the sample size is 1. Well, that's weird. X bar is still the 210. One person selected at random is a sample of 1. Okay, well, let's go for it. Plugging everything in with n equals 1. Hey, what's going to happen to the probability now if we decrease the sample size? Well, it's going to do the opposite of what happened before. The chances are going to get higher in the end. But let's see the numbers. So we plug in our square root 1. Well, hey, square root 1 is 1, so really this is just 25. And always a good idea, just confirm that you get that z-score by yourself. On your own, I should say. And then, all right, it's still a less than negative 0.34. Let me look that up. Negative 0.34, 0.3669. 0.3669. And yeah, wow, okay, so over 36% chance, and this was like not even 2% when we had a sample of 40. So when we dropped it to a sample of 1, if we're just picking one individual, obviously the chances are pretty high that we're going to get somebody who consumes less than 210 pounds per year. Far from a guarantee, but there's a lot of people, over a third of the country consumes less than 210 pounds of meat per year. Hey, wait a second. If n equals 1, the square root of 1 is just 20. Haven't we really just used the formula from chapter 6? I mean, X bar, we're calling it a sample average, but it's just one person. That's not really, I mean, I guess it's an average if you took an average of one thing, but that's just like an X and then our mu and our sigma, and we don't need to divide by the square root of 1, So it turns out, this is like fascinating. Turns out this new formula we learned really is just one level deeper than what we did in chapter 6. In chapter 6, you could argue we were just always taking a sample of 1 and doing this formula, and now we really see it. So we expanded our understanding of the z-score in this formula in the first place. Okay, so hopefully that just like blows your socks off. All right, let's stop this video here, and we'll continue with practice 4 and 5 in the next one.